Okay, everybody, you guys have learned now about graded potentials, that they can depolarize, hyperpolarize, that they must migrate and hopefully make it to the axon hillock, and they must summate at the axon hillock, reach a difference in or change the resting membrane potential, let's put it that way, by at least 15 millivolts in order to trigger the opening of the voltage-gated ion channels. The voltage-gated sodium ion channels must open in order for an action potential to fire. So let's now take a look at the details of an action potential, and we do that by means of a graph. So let's say this is our y-axis, which is our membrane potential, and the membrane potential is always expressed, as you know by now, in millivolts. That means 1,000th of a volt. On the y-axis, we're going to see time, and we express that in milliseconds. In other words, thousandths of a second. So if this is 0.0, we could perhaps say that this is approximately 1 millisecond, 2 milliseconds, and so on. Let's indicate where we would assume to be our resting membrane potential on the y-axis. Let's say that this is equivalent to our resting membrane potential of minus 70. Let's indicate by green and a dashed line the threshold voltage of minus 55. Again, we see a change of, or a difference of 15 millivolts between minus 70 and minus 55. We're going to add a couple more numbers, and that is, let's just add 0.0. And then we're also going to add that point where the difference from minus 70 is 100 millivolts. So if we cause depolarization to occur to where there's a change in the resting membrane potential of 100 millivolts, we would reach about plus 30. And let's just, I don't think the scaling that I've drawn here is very exact, but we're just trying to get a point across. Action potentials are usually going to peak out at the point where there is a difference of 100 millivolts between the resting membrane potential and the peak of the action potential. So with that in mind, let's take a closer look at how this all works. So let's go back to light blue, which is what we used earlier for graded potentials. And so let's assume that we're at the axon hillock, and slowly but surely our axon hillock is depolarizing due to the arrival and the summation of graded potentials. The moment the graded potentials depolarize the axon hillock to minus 55, those sodium voltage-gated ion channels open up, and very rapidly pretty large quantities of sodium rush in, relatively speaking that is, and we almost immediately reach about plus 30 in our example, at which point the polarity of our membrane is so reversed. As a matter of fact, the inside of the axolemma is so positive now compared to the inside that it literally becomes impossible for more positively charged particles to move in to the axon. And so what we see happening is that our sodium gates start to close. The sodium voltage gated channels, or the gates, begin to close. I'll just abbreviate it as such. And instead, what we see happening is that potassium gates begin to open. And we see that potassium follows its concentration gradient, meaning that it flows out of the cell. And as it does that, it takes with it positive charges, And so therefore we're very quickly going back to the resting membrane potential of minus 70. Interestingly enough though, the gates for the potassium gates are very sluggish, and so they take a while to close, and for a very brief moment we see that a little bit too much potassium tends to sneak out of the cell, and we call this point the undershoot. So we see a very short time of hyperpolarization occurring as part of our action potential. But very quickly we go back to our resting membrane potential. So this is what one action potential looks like. Notice that one action potential always consists of the ascending limb, which represents depolarization, which starts right at the point of the threshold, right here. And there's always the descending limb, which represents repolarization due to the efflux of potassium. And we see a little bit too much potassium leaving due to the fact that the potassium gates are slow to close. A couple more things to mention, or maybe to reiterate. The threshold is the point at which the inward flow of sodium, due to the depolarization that is beginning to occur here at the axon hillock, equals the amount of potassium that is flowing out of the cell. So the inward flow of sodium equals the outward flow of potassium here, and that seems to be the triggering point for opening the voltage-gated sodium channels. So here we see the sodium influx due to the opening up of voltage-gated sodium channels. One more time, the reason why we see the sodium gates closing at this peak here is due to the fact that the inside of the cell membrane has become so positive that no more positively charged particles can enter, and instead we start to see that the potassium voltage gates open and potassium particles begin to leave, leading to repolarization. And so this is what a typical action potential looks like in the nervous system and even in the muscular system.